come back. Okay, so my name's Dave Rowland. I'm the Director of Software at Audio Squadron. We have brands like Traction. We make a DAW called Waveform and a whole bunch of plugins and synths. We have Prism Sound, which make high-quality audio interfaces, and the Sadie Digital Audio Workstation as well. A couple of quick notes before I kind of jump into this today. A few questions to start with. Timo did ask, but I couldn't quite see the show of hands. Who here does audio programming? Okay, the majority. Who does real-time audio programming? Oh, that's actually less. Okay. What? Well, we're sort of defined that. Well, we already did. I'll come back to that. Who uses Juice? Okay, not so many people. There's quite a bit of code today, but try not to get bogged down in the details because it's really the concepts that I'm talking about, but I need some code to back up the examples, to back up those concepts. So, well, it's one spoiler, actually. There isn't a right answer tonight. This is how you do this thing. This is how you think about this whole group of things. So did anyone see me and Fabian give this talk at ADC? Couple of people. Okay, if you haven't seen it, I know I'm sort of self-promoting, but Fabian's part of this as well, and he's really good. Go and watch it because it gives a really good primer on what real-time really means and some good paradigms to follow. So a bit of background for this talk. When Timo said, do I want to speak about something, I thought, oh yeah, there's this thing that I've kind of been working on that some people might find interesting. And it sort of stemmed because I was slightly bored one day and reading the Juice forum. And Rusty Pine sort of brought up this situation where he said, hey, trigger async update can get called from the real-time audio thread, and is this problematic? And there was a bit of conversation after this, and I sort of said, well, has anyone actually measured this? Have we tested whether it is real-time in practice? So Jim did the hard work. He ended up testing the time it takes to call effectively trigger async update, and he ended up with this number of 47 milliseconds. So does anyone know roughly how long an audio buffer is? 2-ish milliseconds, give or take, depending on your buffer size sample rate. That's a lot smaller than 47 milliseconds. So we have a problem. We kind of need to look into that. So the first thing I did was I went to the MSVC documentation, because this was Windows he was specifically talking about. And I thought, what does post message say? Are there some options you can send to it to say, hey, do this in a real-time safe way? And the answer was no, basically. And there's nothing on here that says it's wait-free, which is essentially the magic phrase that we're looking for. There's also some other caveats in there that say it can fail if the queue is full and things like that. So we kind of need to be aware of those. Although I think, Ed, did you fix that? Yeah, so if you use it in Juice, it's fixed now. I'm going to rewind slightly a little bit, though. Does everyone know what an async updater is? Just kind of abstractly. I had one hand, so not enough. Okay. So the idea of an async updater is that it's essentially a callback that you can trigger lots of times, and at some point in the future you will get one callback. So it's for coalescing lots of notifications into a single action. Does that make sense to everyone? If you do have any questions, just shoot your hands up and I'll ask, because this is basically me rambling for about 30 minutes. Okay, so I thought I'll pick up Jim's train of thought and try and replicate this and figure out how long it takes on a bunch of my machines to call this trigger async update, effectively post a message to the message queue. So this Mac, well, not this one, this one's Timo's, but my Mac did it in worst case around 160 microseconds. This is microseconds on the side here. And these graphs, I'm going to be showing quite a lot. What they show at the bottom is the minimum. You can see on the windows there's a bit of a gap there. The top of the green is the average, and the top of the yellow is the worst case. So we're really interested in the worst case scenario because that's what's going to cause us buffer overruns. Okay, so I then tested via Windows VM on my machine, And I wasn't able to replicate that 47 milliseconds, but I got around 300 microseconds, which still isn't good. If you think about this being called a lot in a single audio callback, you could very easily go over that 2 milliseconds-ish window. And then I tested on a couple of other machines and got kind of similar 150-ish microseconds, but not great, basically. And also, it's worth noting, this was in a test harness, and all I was doing was hammering this function. In a real-world application where you've got lots of things interacting with the message queue, these numbers are probably going to look a lot worse. So this was a slide that me and Fabian showed at our ADC talk on real-time programming. And we essentially boiled everything we spoke about into one statement, which was don't block. And blocking is essentially anything that is a system call or waiting to acquire a lock of any kind. So if we're trying to make something real-time safe, we need to avoid these. So what do we do about this? Well, first of all, we need to understand the problem. So I tried to really figure out what the use case was and why this problem was arising. And it essentially boils down to plugins using the Juice audio processor value tree state and hosts calling set value of parameters from the audio thread. And they do this because if you have a host that has automation curves or someone's moving a slider or something like that, they can queue up parameter changes, they process them all, and then they call your process block. So they're effectively setting your parameters to what they want it to be before they process. Does that make sense to everyone? Okay. But when you do this, this is going to call a callback, which is parameter value change. So anything that's listening to this audio processor value tree state, or audio processor parameter rather, is going to get notified that that change happened, which is kind of what you want. It's a callback. And the real problem comes in when attached control base registers itself as a listener, gets this changed callback, and then ends up calling trigger async update. And this is what Rusty Pine on the forum highlighted. So we're in this case here. If it's not the message thread, then we need to trigger async update. So this kind of makes it thread safe. And the use case here is that if you're writing a plugin UI, you'll have a bunch of sliders, buttons, etc. If automation comes in, changes those values, you need to then update the slider values based on what the actual value is. So that's how this happens. So that's the problem. What can we do about it? Well, we know that we can't use anything that calls post message. We've already established that's not real-time safe. And what that essentially means is we can't use Juice async updater from a real-time thread because that internally calls post message on Windows. So I thought, well, let's propose some solutions. Let's not just kind of bike shed it on the forum for ages. Let's figure out what it takes to kind of solve this problem. And I'm calling this part create a real-time async updater. Okay, so we're trying to get a real-time guarantee from it. Lots of code. Don't worry about it. The left-hand side is the Juice async updater. The right-hand side is the version that we're going to build. And they look almost identical because they are. I just copied the class because I wanted an exact same interface, so it would be a drop-in replacement, and then figure out what it takes to build that, basically. The only other difference is the members are slightly different, which we'll see here. The internals of Juice async updater are kind of like a pimple. You have this message that is internally reference counted, and it essentially holds the state to whether it should be delivered or not. And in the version we're building here, we've got effectively the same thing, just with a different type. Write some tests. That's good advice. So when we're trying to make something better, we need to have a baseline, and we need to figure out how the changes we're making to it affect it. So this was my test. It's the Juice unit test framework, but essentially you just have one method called run test, and then you can just call this function called expect to make sure things are true. And I decided to template this. So we've got two tests. We've got the run async update test with the Juice async updater, and then the run async update test with the version we're creating. And the reason I did this was because it means the interface has to be the same because it's a template. If we start adding methods or changing removing stuff, then this is going to fail to compile. The other thing it means is that the tests that are run on it are going to be exactly the same because it's effectively the same code. So we have this templated function which is going to run the tests, and then we have this templated struct or class that is going to actually be the body of our test. So this is the kind of body of our test. We effectively have two things: send update and handle async update, and we're going to measure the time between them. And to do this, we need a waitable event, which is how we're going to pause our thread to wait until that update has been handled, and we need an atomic to let us know whether that has actually been delivered or not. So that's going to be our test, basically. So in our send update, that's what's going to be called from the real-time thread. It's going to be calling send update. We say, has it been delivered? Reset that to false. Trigger our async update, which is going to post some message somewhere, and then at some point in the future, our handle async update is going to get called. We set our flag to true and signal whatever's calling us on this event to continue. And we're adding this assertion here because this has to be on the message thread. If it's not, then it kind of defeats the whole point of doing it. Does that make sense so far to everyone? Okay. So in our function that's going to actually run the test very quickly, because it's not that important, we create our updater test. We create a performance counter, which essentially we can start on top, stop, and then we get some statistics from that. And we need this atomic flag to tell us when we finished. Because this is multi-threaded stuff, and normally your callback would be happening on the process call, we're going to kind of replicate that with a thread here. Otherwise, we're just posting on the message thread, and that doesn't really make any sense. So in our tight loop of our test, we're going to do it 10,000 times, and then we're going to start a performance counter, send our update, wait on that event for it to be signaled, and then when the update has been delivered, we can continue and stop our performance counter. So what we're measuring here, and this is important, it's different from before. We're not measuring the cost of calling trigger async update anymore. We're measuring the latency between sending an update and it being and the callback happening. Does that make sense to everyone? Okay, because that all the graphs from this point onwards basically going to be showing that. Okay, we have a test just to check whether it has indeed been delivered. Otherwise, obviously, the test has failed. We've broken something. And then while we haven't finished this test, we just have to pump the message loop to make sure these messages get delivered. Okay. So this is a kind of quick conceptual idea of what trigger async update does. If we think about time moving forwards in our application, we can call trigger async update, and then we have two important characteristics we need to measure. The first is the trigger async update cost, which is how long it takes to call this function. And then the second, when we receive our callback, is the time between them. I kind of just mentioned that, but that helps to kind of cement it. So it's that round trip latency we're looking at here. With the Juice async updater, we can see roughly an average of 20 microseconds, a minimum of 5 microseconds, and a maximum of around 100 microseconds. And if we stick that on a graph, we can see it looks like this. See this gap here? That's our minimum and our average and our maximum at the top. So that's our baseline. That's the performance characteristics that are currently being used in the attached control base. And we're going to figure out what deviations from that happen. So we need to implement this real-time async updater now. As I said, most of the internals are almost identical, but instead of doing this atomic setting and posting, we're going to combine all of that into a single post update call because the logic gets a bit different. So our internals of our message look like this. We are real-time async updater message now. We need to know about our owner because we need to call its handle async update callback. We need this atomic because we're going to be firing it from different threads, whether that callback should be delivered. And this is the main difference here. Before we were using post message to kind of use the system queue to call things back, but now we need to handle this ourselves. So we've got this shared reference to what we're calling a dispatcher, and that's going to be responsible for actually calling our callbacks. So we need to register and remove ourselves from the dispatcher. Then we have this post update that all it's going to do now is call set on our atomic. So this is the key difference. This means this is now real-time safe. Remember before, this was calling set for the atomic and then post message, and that was causing all the problems. Now we've removed that. So we know this is real-time safe. At some point in the future, our dispatcher is going to come round and call service message, and it's going to check the value of this should deliver flag, and if it was set, we'll reset it and call our callback. Okay? Any questions on that? One at the back?
Not at that one, but the step before. Why are you interested in the round trip cost? Because that's actually not real time. That's just a GUI update, which is we actually don't care. It just should happen like 35 milliseconds before the next visual phrase happened. But we're only interested in the audio real time.
Okay. So the question is, why are we measuring round trip latency? Yeah. And the answer is because that's the thing that changes. As we do different approaches to things, we're going to change the performance characteristics. And you say, yeah, we're doing UI updates. For this example, we are, but we're changing a library function to make something else. So the point is, we need to consider how things are changing. And that's what I'll dig into a bit, okay? So, trade-offs. We now have a real-time safe way of posting a message, but how do we service these messages? We need to kind of call the callbacks some way. We can't use system calls, as I mentioned. We need to manage this ourselves, so we need to implement the dispatcher. And that means we have to decide what's acceptable. Yes, you might be able to do it in a kind of 25 frames per second way, but that might not be good enough for some other async updaters. I know we have use cases where we use juice async updater, and doing it on that kind of frequency just wouldn't be responsive enough. So we have to decide things about this round trip latency. We have to think about CPU overhead. Does that change? And the ordering of callbacks, which may or may not be important, and I'll come back to that later. So here's the first stab at implementing our dispatcher. We're going to have an array of updaters. So these are the messages that get registered with us, and we need to be able to add and remove them. And then we're going to implement from timer and then start a timer at 25 hertz. This basically is what you were saying a minute ago. So we've already chosen here a characteristic about how this dispatcher is going to behave. We're saying it's running at 25 hertz, which is roughly 40 millisecond intervals. That might be okay, might not be okay. Maybe you want to run at 60 frames per second. You're already making hard decisions at this point. And then when the timer callback happens, we're going to call service updaters. So at some point, when this timer calls back, we're going to iterate through all of our updaters and call them. So here's the add and remove. They're not very interesting. And then service updaters, we're just going to take this lock so we make sure we're not modifying the array as we iterate it. And then we're going to call service message for all of our updaters. As you can see here, this is one of the first problems we have, in that because we're iterating this updaters array, we're always going to call the callbacks in the order that they get registered, which is a different characteristic from the juice async updater. And that may or may not matter. If you've got a bunch of sliders on the screen and you just want them to, at some point in the future, reflect the true value, probably doesn't matter. But certainly when you're doing things like using async updaters with value trees, it almost certainly does matter. So our service message simply checks the value of our atomic, as I mentioned before, and calls the callback if necessary. So this was our juice baseline, remember? This is our timer-based real-time async updater, and here's the difference. Our average before was 20 microseconds. Our average now is 40 milliseconds. Minimum was 5 microseconds. Now it's around 200. And the maximum before was around 100 microseconds. Now it's 92 milliseconds. So we've completely destroyed the latency that we had before. And if we stick that on a graph, we can't even see the juice version anymore. It's massively different. So you can see how we've changed the behavior here. And that makes sense. We've started a timer here, and we've started it at 25 hertz, which is around 40 milliseconds. So we can think in terms of time running through our application. In our test case, we've basically started by calling post update, waiting for the timer to call back, and then call service message, and then almost immediately posted another update, and then waited for service message to get called on the timer callback, and so on. So you can see we would expect this to average out at 40 milliseconds, and the timers aren't spot on, which is why you kind of get that huge variation. But this isn't really how a real world use of this would look like. You'd probably end up with a lot of trigger async update calls. So what you'll probably get is an average of around 20 milliseconds with a jitter of around 40. So what we've done is we've engineered a solution which has an average latency, in this test case, of 40 milliseconds and a jitter of around 80 milliseconds, which isn't anything like what we had before. We've got an additional overhead that a timer's now running, and that's going to be continuously running. And if you have an application with lots of timers, perhaps that timer running is going to introduce a cost there. But it is real-time safe, and that was the whole point of this. So you can hammer it from any background thread with effectively no cost. And as I mentioned, the callbacks will happen in the order that the real-time async updaters are created, and that may or may not be problematic. So can we do better than this? Well, there's another approach, which is to implement our dispatcher, which is to use a thread, essentially. I'm going to hide all the bits that haven't changed. So in this example, we're inheriting from high resolution timer, which internally runs a thread that has a waitable, or it just blocks a thread for a specific period of time and then has a callback. So we still have start timer, but this is in milliseconds now. And I thought, well, we're running a background thread, so we're kind of moving the overhead from the message thread, which could grind your application down, and we'll make this 5 milliseconds. We have our high-res timer callback, but this happens on a background thread now, so we need to use the juice async updater to call trigger async update, which at some point in the future is going to come around and call handle async update, and then we can service our updaters. So one of the performance characteristics you might notice about this is its best case is going to be as bad as the worst case from before, because you're still using the trigger async update to get things onto the message thread. But it's real-time safe. And also, there was some overhead because we were always calling trigger async update every time a callback, but actually we only want to do that if anything has actually triggered the callback, so we can introduce this new atomic to see whether it needs to service any updaters and set that in this signal method. And that changes what our post-update method looks like a bit. We have to set the flag, but now we have to call this signal method. And then when we call back, we just check this, reset it, and if it was true, call trigger async update. Okay, so what does that look like in terms of performance characteristics? Well, now we have this very steady average of around 5 milliseconds, minimum just below it, maximum just above it. So we've got a very rock steady timer interval now. It doesn't quite have the jitter that we had before. So we've got much more stable latency, and because we're using the background thread and I chose that 5 millisecond number, it's a lot lower than it was before. And that's what it looks like on the graph. So you can see much lower but much more stable as well. But we're still not seeing it to be relatively comparable to what Juice was before. So if we summarize, we've engineered a solution which will have an average latency of around 2.5 milliseconds with a jitter of around 5 milliseconds. It requires an additional thread to be running. Again, we're talking about a library class here. So do we want to be spinning up threads to service these dispatchers? You need to think about that. It's relatively low CPU overhead though, apart from the thread running. And it is still real-time safe because we're only setting that atomic from the message thread. So to recap, we've created two solutions which are real-time safe. They return instantly from trigger async update, which is good. But both have additional overheads. We've kind of moved them around from the costs of calling the callbacks, introducing threads, etc. But they both have worse average latency than Juice async updater. And that is going to be important when you use it in your application. So, but it seems like what we're doing is essentially engineering a really complicated solution to just getting a slider to change its value when an internal value changes. So perhaps this isn't the right approach. Maybe we should be thinking about something completely different. But then I thought, well, is there a way to get closer to the characteristics of juice async updater with making some other trade-offs? And in this instance, we're implementing our dispatcher, but instead of inheriting from a high-resolution timer, we'll inherit directly from thread. This gives us more control over its characteristics. So we're going to start our thread, and this just uses the default priority, which I think is 5, but could this be lower? Does it need to be higher? Again, that's something that you need to think about. And while our thread's running, we're just going to make sure that we're not destructing. That just avoids a potential hang-on load. And we're going to wait on this waitable event. And then essentially what's going to happen is when messages need to be posted, they're going to signal this event. Then we can continue from this point in the thread, call trigger async update, and then at some point in the future, we're going to service our updaters. So we can see that this waitable event here is going to be wait and then signaled. Does that make sense to everyone? It kind of works like a latch. Okay, and in the same way before, when we call post update, we need to set our flag and then signal the dispatcher, which is going to signal this service event. Let's have a look at the performance characteristics. We can see that we have an average now of 20 microseconds, minimum of 7 microseconds, and a maximum of around 7 milliseconds. Okay, so that's our round trip latency again. And if we stick that on the graph, we can see how that's very different from the two previous solutions. We're now, on average, about comparable to Juice. And if I get rid of the timer because it's kind of skewing the graph, you can see how on average it's very comparable. It has a slightly worse case scenario, but that could be introduced by the Juice async updater, or perhaps a long time for the thread to wake up. But waitable event, can we use that in a real-time context? So let's summarize that solution. We've made a low latency version. It's comparable in terms of performance to the Juice async updater. It's low CPU overhead. It's essentially just got an additional notify all cost. But that means it's not thread safe because we've used this system call. We're interacting with the thread scheduler. And as we know, we can't do that if we want to have real-time guarantees. And also, we still have this problem that it requires an additional thread to be running. So the signal call on the waitable event ends up going through a stood condition variable notify all, as I said, which is a system call, and because that interacts with the thread scheduler, it could block, and that means it's not real-time safe. So perhaps this isn't, or we shouldn't call this a real-time async updater. Perhaps this should be named something like low latency async updater, okay? Because that better describes its performance characteristics. But if we actually go back to our original case where we were measuring how long it takes to call the trigger async update call, we can kind of compare these things. So the Juice one had this high worst case. Remember, this is the call of triggering the async update now. And you can see this was the problematic bit at the top here. The two solutions that use the atomic in the middle are very good. And the waitable event is actually comparable to this. So you might think, well, actually, can we use this? This gives us all the benefits of the low latency version, but is kind of nearly perhaps real-time safe. Would you use it in a self-driving car or a plane? Probably not. Would you use it on a general purpose laptop running plugins? That's for you to decide, really. I think what this shows us is we need to measure real-world cases more and figure out what the different performance characteristics are, and also be aware of your use cases. So that's kind of it. I said there wasn't going to be a real final solution. It's going to be a series of questions. And here's essentially the things that we've kind of traded off as we've kind of gone along. Real-time versus non-real-time guarantees. Library-created background thread versus timers that are running. Minimum latency versus jitter versus additional CPU overheads. And maybe what we've actually done is created a solution that isn't really suitable for a general purpose library. Maybe the attached control base should just run its own timer and just check for values internally. That would be real-time safe, and it wouldn't kind of impose all these predetermined characteristics on us. But the message here really is to think about your use cases and trade-offs. For a lot of people, as Daniel said, we're just running a timer to refresh the screen. That's fine. But if we're trying to make something real-time safe and put it in a library, we need to think about what are all the ways people are going to use it and how to describe the performance characteristics. And I mentioned there was a few problems. We had the order in a callbacks problem, which again may or may not be problematic. Rowland Rabin, who works with me at Traction, instantly we ended up, for fun, looking at this problem on the same day and coming up with almost the same solution with the condition variable. And he solved the ordering problem by having a counter that just gets atomically incremented, and then each of the update messages take a number, and then when you dispatch them, you can sort them in the order that they got called in. There's another approach as well that you could use, a lock-free queue. So you kind of push them into a queue, and then your dispatcher empties the queue. So there's lots of different things here, although I didn't want to dig into them too deeply today. We could think about a template parameter for the timer interval. That would mean that a user of your library could then use a template parameter to have a really fast timer if that's what they needed. But then you need to think about if it's going to be running a thread internally, then every different number for the timer interval is going to spin up a new thread. So you're kind of messing with stuff there. Just things to think about, really. So that's it, I'm afraid, or you'll be glad. Well, are there any questions on that? One question here.
So I have a question. So you said condition variable notify all is a system call. Well, obviously, at least it has to like lock a mutex. So maybe it's too generic of a question, but like, let's say we are producing audio, right? We're like on the audio callback. We're actually pumping stuff out over the speakers. When is that fine to do that? Like, do you have any kind of advice on that?
Define fine. Do you get away with it?
Like, none of my users will ever say your product doesn't work because it glitches.
Well, they might, and that's what I would say why we can't accept that as a solution to this. But if all of your production code ever uses this and it's never a problem, then was it really a problem to start with? It's about your guarantees, really, and can you measure it? I would say lots of people probably are doing stuff like this, but they might also have plugins or audio code that occasionally drops out, and people never notice. Maybe they correct it in post. I would say advise against it. Use a real-time safe solution if you want to be real-time safe. But as a characteristic that's similar to the Juice async updater, but doesn't have that 47 millisecond occasional overhead, it's probably the most similar but performing slightly better. So maybe you want to do that first and then think about your system in terms of making it real-time safe. Because the other thing here is what I hope this summarizes is making something real-time safe isn't like clicking your fingers or flicking a switch and just suddenly it's all real-time safe. It really means that you have to think about how your problem works differently. And going through this process helps you think about this and go, well, yeah, this probably isn't acceptable. I don't like this timer. This isn't quick enough in this solution. So you kind of really need to engineer your system slightly differently. Any other questions? Okay, thanks very much then. I'll hand back to Timo.